Hi, my name is Ian Barnett. I'm an assistant professor of biostatistics at the Department of Biostatistics, Epidemiology, and Informatics at the University of Pennsylvania. Thanks for having me today at the Computational Data Neuroscience Symposium. I'll be talking about smartphone-based digital phenotyping. In particular, I'll focus on the kind of methods we have developed to handle this kind of data, as well as a variety of applications we've used it in. So, what can digital phenotyping do? Digital phenotyping is when we passively collect smartphone sensor data to measure patient behavior. And then once we've measured patient behavior, we want to then connect it to a clinically relevant outcome. So the kind of behaviors we measure are physical activity, social activity, interaction, sleep, mobility, routine, in addition to self-reported clinical outcomes. If we think about the kind of methods we use to analyze this data, you can really break it up into two stages. Because to start with, smartphone sensor data is really noisy and messy. It has a lot of missingness in it. So it's not immediately useful. You first have to kind of process and analyze it to create a meaningful measure of behavior. So once you have that meaningful measure of behavior, and sometimes through this talk, I'll interchangeably use measure of behavior and feature. So once you have these features or measures of behavior, we want to connect them to a clinically relevant outcome. Now that's of course the interesting part, bringing it back to the clinical outcome. But you can't skip over that stage one. You have to handle that noisy data first. So I'll talk about how we approach modeling in stage two as well as modeling in stage one. So a standard digital phenotyping study runs like this. We install an app on a patient's smartphone and it collects all the sensor data, as you can see, in a variety of domains. We measure behavior. So you see these domains of behavior, which we kind of gather from a variety of sensors, and then once we take that raw data, we try to convert it into this matrix down below. You see at the bottom here, this colorful matrix. So in this matrix, each column represents a different day, and each row represents a different feature or a different meaningful measure of mobility or sociability or sleep, etc. And so once we have this matrix at the bottom, that's when we can do our nice analyses, but we have to get there first. So one approach I'll talk about in this stage one approach is taking this GPS data, which has a lot of missingness in it, and converting that into meaningful measures of mobility. So if you look at this top panel, you can see this is GPS data for someone collected over a week. And you can kind of see how there's little gaps in their commute from home to work. Home is in the blue, work is in the red. So there are gaps in the data simply because GPS takes a lot of battery. You can't have it running 24/7. Therefore, it has to be collected sporadically. But what we do before we can calculate any meaningful measures of mobility is we first have to fill in those gaps. So we developed a multiple imputation method which fills in the gaps, and that's what you can see down below, where we see more or less complete trajectories of a person over the course of the day. And once we have these complete trajectories, now we can go and calculate things like distance traveled, time spent at home, etc. And these are, really intuitive measures of mobility which we can then use in stage two analyses. All right, another stage one kind of analysis is how do we handle call and text logs to measure sociability? So call and text logs can be used to construct egocentric networks, social networks. And in some cases, we actually will also have call detail records, which can provide richer community level social networks. And when you have, large social networks, and it's actually not just social networks, this applies to across network science and many domains where you have different kinds of networks. But one of the first things that a network scientist will do is look to see if there's meaningful community structure. And one way of quantifying that in a network is a statistic called modularity. And this is really commonly used, but there's very little known about what its null distribution might look like, right? And so what we've done is we've derived its asymptotic null distribution. This enables scalable hypothesis testing in large networks. So I've talked about two kind of stage one analyses. Let's talk about a stage two analysis. Once we have this feature matrix, what's something we can do with it and connect it back to something that's clinically relevant? So I'll talk about change point detection. I'll talk about a specific application, and this is to patients with schizophrenia. And what we wanted to do was see if there was a significant change in a person's behavior or anomalies in their behavior as measured by their passive smartphone sensor data. And if those changes and anomalies in behavior were at all connected to their relapse and hospitalization. And what we actually found was that there was a 71% increase in the rate of significant behavioral anomalies in patients with schizophrenia in the 2 weeks prior to hospitalization and relapse than compared to when things were normal. So much higher rate in anomalies. And furthermore, we also went back and looked at some of these patients that were hospitalized, and we wanted to see, looking only at their smartphone data collected pre-hospitalization, could we have anticipated this? Could we have seen this coming using only passively collected data? And the answer was actually yes. I'll give an example here on the right. You can see this is from one patient. These are 3 different digital phenotypes, but the vertical red line is when they were hospitalized. And this is actually in the 7th week of follow-up for them. And the vertical dotted orange line is when we detected there was a significant change point. And so you can see, using only the data pre-hospitalization, we actually detected a significant change point about a week before. So, this has immediate implications for things like interventions, etc. So I'll also talk about more directly predicting clinical outcomes using this feature matrix. So longitudinal prediction with neural networks, this is kind of fairly cutting edge, because there's classic statistical models for longitudinal modeling, but they're not the best at prediction. So the state-of-the-art statistical modeling for longitudinal data is generalized linear mixed models, but they're kind of restricted by this linear fixed effect. So the predictive power can't be that great, even though it does a really good job of allowing for kind of personalized modeling through the random effects. Now, on the other hand, we've seen definitely in the past 10, 20 years, neural networks and deep learning have really taken off and shown the predictive power they can have when you have a rich feature set. But neural networks are a population level model. By the fact that they're highly parameterized is precisely the reason why you cannot have individual level parameters. They're not personalized. So how do we take these really powerful predictive models that are their population level predictive models and kind of take the advantages of something like a GLMM, where we have really nice individual level modeling, and merge them together? That's what we did with something called generalized neural network mixed models. So what we wanted to see is, these are with patients with depression and anxiety. We wanted to see how good could we predict their depression, how good could we predict their anxiety using purely their passively collected smartphone data. And you can see here that our approach, GNMM, actually outperformed the competitors. But more than that, I want to actually point out just how good of the predictions they are. Let's look at anxiety. So anxiety was scored from a scale from 0 to 3. And we're actually seeing a mean squared prediction error of 0.062. That's incredibly precise. What this is telling us is that we don't need to ask them about their anxiety. We could just look at their smartphone data, and we can get incredibly good prediction by having both the complexity that neural networks allow us in our prediction, as well as learning about a person's history. Combining those together, we can get incredible prediction. So now I'll take a step back. This is another stage 1 analysis we've done, is taking phone usage and estimating sleep from it. So if you look here at the top, you can kind of see phone usage. This is screen on-off data. What's unobserved, of course, is when someone falls asleep and wakes up. And that's what we're trying to estimate. So we've developed a modeling approach which essentially treats this as a latent variable and does a fairly good job of estimating when someone sleeps and when they wake up based purely on their phone usage. Of course, this is going to help more for people who use their phone more. In populations where you don't use your phone a lot, this method won't help, but that comes with the territory when it comes to digital phenotyping. And you can see for this example, this is actually a teenager with borderline personality disorder. And, so a teenage population, they're going to use their phone a lot. This method's going to work very well on them generally. You can see this patient goes to bed about 11 p.m. every night, plus or minus 1 hour, wakes up at 7:30 every morning, plus or minus 1 hour. Pretty high correlation between when they go to bed and when they wake up, which kind of makes sense. And then they use their phone about 6 times as more often when they're awake than when they're asleep. I will comment, you might wonder at this point, how can they possibly use their phone while they're asleep? Well, what we say is, if you wake up in the middle of the night and you go on your phone, that's still technically in their sleep interval. What that's going to do is it's going to influence the number of sleep disturbances they had, which we also measure. But anyway, if you were wondering how this could possibly be anything other than 0, because it wouldn't make sense to use your phone while you're asleep, that's why it's allowed to be something positive. But of course, it's going to be smaller than what it is when they're awake. Finally, I'll talk about tracking postoperative recovery. And we can see here that there's an inverse relationship between a person's mobility after having surgery and their self-reported pain. And the implications of this are that if you want to track someone's recovery, maybe we could just look at these passively collected measures and they can do a decent job rather than putting the burden on the patient to tell us how much pain they're in, say, every day. And this picture is a nice example of seeing that inverse relationship. So these are just a couple of topics, a non-exhaustive list of applications of digital and phenotyping, but just to give you a taste. And if you're interested, please reach out to me. I'd be happy to talk more. And I want to thank the NIMH for their generous support as well. Thank you very much.